So these are the questions which will be answered during this talk, that what is a stress and strain diagram, what are different reasons in this diagram, and what are their underlying genesis or causes. So before moving directly to the stress and strain diagram, let us first understand stress. So engineering stress, or which is commonly known as stress, is the internal resisting force per unit area. Here area is the original cross sectional area. So if P is the applied load, A is the cross sectional area, so P by A gives rise to the stress, which is denoted by the Greek letter sigma. So this can be understood easily with the help of this schematic. So this is a horizontal bar which is subjected to the actual load P. So on the right side as well as on the left side, so this its tendency is to increase the length of the bar. So it is a tensile loading. So consider a imaginary cross section XX. So if you cut our bar from this imaginary cross section, and if we analyze the left hand portion of the bar, you can see that on the left hand side of it we have the externally applied load P, but on the right hand side you can see there are array of arrows which have been placed, and these arrows represents the internal resisting force, because the bar will try to remain in its equilibrium position, so it will resist the deformation due to the externally applied load, and internal resisting force is equal to the externally applied load P. So that is why stress we write as the internal resisting force divided by the cross sectional area. And if suppose if you have applied sufficient amount of load such that its length increases, so change in the length, which is delta L divided by its original length, give rise to this strain, which is a dimensionless quantity. So in order to test a material to determine its strength, we perform a test in universal testing machine, which is known as the tensile test. And this universal testing machine is commonly known as UTM. So this is the frame of the UTM, and here we have two grips. One, the bottom one is fixed and the top one is movable. So these are the typical specimens, how they look like. You can also use a flat specimen or round specimens, and these specimens should be in conformity with the ASTM standards. So when you hold your specimen in between these grips, the movable grip moves in the upward direction, so that, and the bottom will remain fixed, so it will extend this sample and will get the force elongation curve. So here one point can be noted, that if you take suppose round specimens of different length and diameters, so you will get different force elongation curves, because the higher diameter specimen will require higher force for the elongation, so you will get different curves for same material. So in order to normalize it, what we will do, if you divide the force with the cross sectional area and elongation with the length, we'll get a term, or we'll get a graph which represents stress and strain, and this will remain same for one material no matter which type of sample you are using, uh, provided they are according to the STM standards. And this is a schematic diagram of this specimen if you have to look. So this is a flat specimen. These are also known as dog bone specimens. This is the width of this specimen, diameter of this specimen, and this is the gauge length, which is the area under the observation. And this is the overall length of the specimen. So these circular sections here are provided to avoid any stress concentration, so that specimen should not break from here. So now let us move to the okay, so this is the picture where it shows the grips in actual way, how they look like in a UTM. Now let us move to the stress and strain diagram. So here the y-axis represents stress, and in Newton per mm square or MPa megapascal, and x-axis represents strain percentage. So here these different points have been marked or written properly here, although I will explain it as we will go point by point. So from O, we are starting testing the specimen. When you are increasing the load, you will get a straight line up to OA. This is known as the proportional limit. Means as you are applying the the strain is also increasing, and you will get a straight line, and this slope of this is known as the modulus of elasticity E. And if you increase further, you will reach up to a point B, which is known as the elastic limit. Means if you will load the specimen up to the point B and unload it, the specimen will come to its original position or original length. So A to B, here it is slightly curved, and this A and B sometimes they occur at the same position. So it depends on the accuracy of our measuring instruments, how accurately we can measure strain. So here C and D, these are the yield point. Yield point is known as the onset of the plastic deformation. So C point is known as upper yield point, D is the lower yield point, and D to E is known as the yield point elongation. At point C, these dislocations, the plastic deformation occurs due to the movement of the dislocations. C marks the onset of the plastic deformation. So at C, what happens is dislocations are trapped by impurity atoms, so they do not move easily. And when you apply a sufficient amount of load, they suddenly became mobile. So the stress decreases up to the point T, and when they become mobile, they just move easily without any appreciable amount of increase in stress. So this is known as the yield point elongation, and stress here is assumed to be a constant, although it is varying very slightly. And E to F region is the strain hardening region. So as its name suggests, in this region strain is hard to produce, means you have to increase stress in order to produce strain, and this occurs due to the dislocations pile up. So assume you are aware of the dislocations. So edge dislocations is example of one example of dislocation. So when dislocations pile up over one over the another, then you require higher amount of force in order to, or stress in order to move this, and this marks this reason. And F, at point F, it is known as the UTS, or ultimate tensile strength, or ultimate stress which the specimen can bear. And at this point, necking starts, and necking is the localized decrease in the cross-sectional area. And when the area decreases, so stress which is required to cause further strain decreases, and the specimen fractures at point G. So suppose if I am loading this specimen up to the point, this red point, and I'm unloading this specimen, then what will happen? So if I'm unload this specimen from this red dot, then this specimen will unloading curve will follow this red path parallel to the proportional limit. So this up to this point O, there was the total strain was OH, but when you unloaded it, the strain which you can observe or which you can see is only up to OI. So the total strain here up to the OH has two parts. One is strain which is elastically recovered during unloading, and one it is permanent set. So I to H is the elastically recoverable strain, and it is the plastic strain or plastic deformation. So this was the example of ductile material, and this is the typical curve for the mild steel. We have chosen the mild steel because it shows all the prominent points. Now there are brittle materials. So brittle materials are the materials which do not show appreciable plastic deformation. Their plastic deformation is very less. Now, you do not always get a curve which shows distinctly all these points. So sometimes, most of the times we get the black curve which is shown here. So the material like aluminum, titanium shows this curve. So here these do not show yield point. So for yield point, we have to use offset method. We calculate total strain. We take 0.2% of total strain. We mark it on the horizontal axis, and then we draw a straight line, and wherever it intersects the black curve, will mark as the yield point. So this was all about the stress and strain diagram. Hope you have got enough from it.